Hello everyone, welcome to all of you in my lecture today. Here in this session, I'm going to teach about the condensation heat transfer. So basically, I have discussed about the evaporation heat transfer in my previous lecture. So you can go and watch to that lecture also. So evaporation, condensation is also a unit operation. So in condensation, what used to take place, in this unit operation generally the vapor that is coming in contact with the cold surface and that will get converted into vapor to liquid. So here you can see, so there will be a cold surface and the temperature of this cold surface will be less than that compared to the temperature of that vapor. Okay, so I'm assuming this is a cold surface, right? This is cold surface. What will happen if this vapor is there? Okay, if vapor is coming in contact with this surface, what will happen? This vapor will start to getting converted into vapor to liquid. So here what will happen? Vapor will be getting converted into liquid. Why? Because when this vapor, since if I am assuming the surface temperature is Ts and the temperature of this vapor will be T, right? That is at the saturation temperature I am assuming. So I am writing that is saturation. So if T surface is less than T saturation temperature, then the condensation will take place. Which is getting condensed over here? This vapor will getting condensed into the liquid. So, my dear student, there are two types of condensation operation is there. That is film. One is film-wise condensation, and second is drop-wise condensation. So, in film-wise condensation, what used to happen? Generally, I am taking that is a vertical plate, right? So I'll let you know why I'm taking vertical plate and all after some time. So this vapor is coming over here. So this vapor will be coming, and here the temperature of this is Ts and the temperature of this vapor is T saturation, right? So it will come in contact and it will try to get condensed over here, right? So it will try to get condensed over here. So in film-wise condensation, what happens over here? This vapor get condensed over here and it will blanket this surface, right? So it will totally cover this particular surface over here, right? So in the form of film. So that's why it is known as film-wise condensation. But when it comes to the drop-wise condensation, what will happen? In drop-wise condensation, the vapor will be coming in contact with this surface and it will be getting like that. So it will form a drop on this particular surface. So here you can see here there is completely film that is going to deposited on the surface of that surface, but here there is a drop in the vapor is getting condensed in terms of the drop. So there is extra area surface. You will always see there is extra surface available for the condensation of this vapor into the liquid on in drop wise condensation, but there you won't see there is always area for the condensation for this vapor on this particular surface. So, generally, the heat transfer coefficient for the drop-wise condensation is 4 to 5 times heat transfer coefficient for drop-wise condensation, that is equals to 4 to 5 times that is heat transfer coefficient for film wise condensation. Means rate of heat transfer will be more in drop wise condensation compared to the film wise condensation. But the problem is that it is very difficult to maintain drop wise condensation in reality. That's why it's obvious to use the film wise condensation for the design purpose of the condenser, right? So this is the basic reason that why we use film wise condensation for the industrial application, not drop wise condensation. Why? Because in film wise condensation it's very easy to maintain, but in drop wise condensation it's tough to maintain irrespective of their more heat transfer coefficient compared to the film wise condensation. Now addition, let's try to understand the pictorial representation of this particular condensation surface and we'll derive the mathematical equations for the condensation, right? Here, so here you can see, if I am assuming this is a surface, right? on which condensation will take place, and the temperature of the surface is T. So my dear student, this vapor will be coming over here because vapor will be at higher temperature compared to the surface. So what will happen here? So you'll see completely. I'm drawing this graph a little bit in this way. Yeah, try to understand the thing what I'm trying to tell you, because it will be very helpful for driving the mathematical equation for the condensation, right? So what will happen, this vapor will come and it will come in contact of the surface and it will be getting in this form. So coming to the surface, so here you will see this will called as the condensate. So it will look like that. This is the pictures of that that, right? So what will happen actually here? You'll have to drive the mathematical equations, right? So to drive the mathematical equations, Nusselt was a scientist or a researcher who has given some assumptions to drive the rate of heat transfer for the heat transfer for the condensation in film-wise condensation. Actually, this is a film-wise condensation, right? Film-wise condensation. So we'll have to study the nusselt theory. So here it is a nusselt theory for the film-wise condensation. You can see here he has given some 4 to 5 fundamentals assumptions that both vapor and liquid are maintained at constant temperature, and heat transfer by liquid is takes place by purely conduction, and velocity of vapor is very low, so that there is no shear force at the liquid vapor interface. Why? So here you can see this will be liquid, right? Now this is liquid. So here this vapor will be coming. So there will be a liquid vapor interface. So velocity of the condensate will be very low. Vapor is very low. So there is no any relative velocity between the condensate and the vapor. So that there won't be any shear force between the liquid and vapor, right? Next assumption is that acceleration of the condensate layer is negligible. So acceleration of this condensate layer is assumed to be very less. That is, acceleration is equals to, generally we can assume that is zero. That is dv by dt, we can assume it is a zero. So that was the Nusselt theory for the assumptions for the film-wise condensation in the heat transfer. So now try to understand the mathematical representation. How we'll derive the mathematical formula for the film-wise condensation radiation. So here I am assuming there is a surface. Okay. So try to understand the representation only. So I am assuming this is y direction, and because length scale is very important for this particular problem, this is x direction, right? So the length of this plate I am assuming is L, right? So since the vapor will be coming, it will come in contact, that the surface temperature of this particular plate is Ts, so it will come and it will be like that, right? So so you can see there will be a boundary layer formations, and the thickness of this boundary layer I am assuming that is delta. That is delta. So I am considering a small element of this condensate liquid. Okay, I am considering the small element of this condensate liquid at a distance, horizontal distance y. Since this is delta, so this is y. So this particular distance, so this particular distance will be, my dear student, delta minus y. Are you agree with this one? And I am assuming this length scale, that is dx, that thickness is dx, and the width of this plate is width of this plate in along this direction is, I am assuming, is w. Okay, so I think up to this you are clear. That is delta x, that is boundary layer thickness. Delta x is equals to boundary layer thickness, and L is equals to length of plate at which condensation will take place, and W is equals to width of plate along Z direction. If I am assuming this is Z direction, this is Y direction, this is X direction, right? So if I am trying to project this particular area over here, this project the particular area, so it will look like that. Try to understand. It will look like that. Wait 1 second. Figure is not exact, but try to understand one thing. So my dear student, this length is dx, and this one is del minus y, right? And this one will be our w, right? So for this particular element, can I write volume that is equals to w dx, and that is del minus y? Agree or not? And thing is that since this is the, I mean, this is liquid condensate, okay? So this mass of this that is equals to rho of liquid into volume. Can I write? So this mass of liquid that is equals to rho of liquid into volume is W dx uh, del minus y. I think up to this it's very clear. I'm simply writing mass is equals to density into volume first, and that is volume is equals to, I'm just assuming it will be like this particular shape and the dimensions of this shape that I have derived from here, and I have written like that, right? So now for this particular element, my dear student, can I apply the force balance, and which force will be acting over here? Try to understand. Which, how many force will be acting? I am letting you to understand. So this dimensions is W, and this dimensions is del minus y, and these dimensions of this condensate layer is dx. So for a particular, I am just assuming this, since vapor will be coming, so it will be experiencing, this particular element will be experiencing a buoyancy force, and due to gravity it will be experiencing a gravity. And since you can see here, this layer is coming from getting deposited on this particular surface, so this layer liquid will be experiencing a shear force due to this particular wall, right? So shear force will be in opposite direction, right? So one force will be F shear force, or that is equals to F viscous force. So can I write, my dear student, applying force balance, right? So I can write F gravity minus F viscous minus F buoyancy, that is equals to M dV by dt. Since already I have told you that the relative velocity between this, I mean, acceleration is assumed to be negligible, so that is equals to 0. So can I write Fg minus Fb minus Fb, that is equals to 0, right? So gravity force Fg is equals to m multiplied with g. M is equals to rho of liquid into W dx del minus y, that is F viscous, that is equals to mu of liquid du by dy, and du by dy, and F buoyancy, that is equals to rho of V, that is vapor density of vapor, rho V of vapor, and volume of that condensate layer, that is equals to W dx w dx and that is del minus y, that is volume v rho g into g. So now we'll substitute this value over here and we'll get some relation. So fg is equals to m into g. So that is equals to w dx del minus y into g minus f by n c rho v w dx del minus y rho v and g minus mu of liquid du by dy. So that is equals to 0. If we can take some common over here, and here it is equals to rho of liquid. So we can take common rho of liquid minus rho of vapor, that is equals to g w dx del minus y, that is equals to mu l du by dy, right? So can I write here du by dy uh, dy that is equals to rho l minus rho v gw dx del minus y and divide. I've done one mistakes over here, so let me complete that viscous force that is equals to here also the area will be multiplied, so that is equals to w dx, right? That is equals to tau shear stress multiplied with that surface area, right? So here I have to multiply it with w dx, so it will be w dx, so that will be equals to mu l w dx. So this w dx and w dx will get cancelled out. So can I write, my dear student, du by dy that is equals to rho l minus rho v g del minus y upon mu l. Mu l. So this is the gradient of velocity of that condensate layer that we have got right now, right? So now I am trying to derive the velocity over here. So my dear student, try to understand. This is condensate layer. So it's like that, right? That I have derived here. So at boundary layer at y is equals to delta, since this is in y direction and this is our x direction and this is our z direction. So at y is equals to delta, du by dy is equals to 0 and y is equals to 0, u is equals to 0 because of no slip condition, right? So these two boundary condition, because we'll have to use these two boundary condition. We'll see which boundary condition is required for the solution of this. So this is our differential equation. So when this difference will solve this differential equation, you will be like you will get. So here I am writing du by dy that is equals to uh, rho l minus rho v and that is uh, rho l minus rho v that is g and del minus y upon mu l. So now solving differential equation, uy is equals to rho l minus rho v g del y minus y square upon 2 by mu l plus c1. So at uh, y is equals to 0, u is equals to 0. This is our boundary condition that we'll have to use over here. So c1 will be equals to 0. So we can get the relation of velocity along the y direction of that condensate, that is equals to rho l minus rho v into G del y minus y square upon 2 by mu L. So it's a very important relation that we have derived over here. So sometimes you will get question on this particular formula as well. So calculate the velocity of the condensate layer at a particular distance from y. That viscosity of liquid is mu L, rho L is density of liquid, rho V is density of vapor, G is density acceleration due to gravity, right? So all these things that having some meaning. So sometimes it will give some approximation if density of liquid is very greater than density of vapor. So neglecting density of vapor, so rho L into G into del y minus y square by 2. So that depends upon the derivation that how we were using, right? So next I think up to this, I'll leave it now for this particular lecture. In the next lecture, I will be deriving the heat transfer correlation and will be deriving the boundary layer thickness for a particular condensate layer. Okay. So thank you and all the best for this.